Yeah, I was actually going to share some things I've been working on with agents, like training agents with some of our readings and things like that, and getting some answers out of it. Um, reconstructing cybernetics, we have a GitHub repository for that. We've been doing things like, defining terms and things like that. So I decided, I would like to train a model with some of the data from different sources and almost kind of build a model that's like ask a cybernetician. So the idea is like I train it on sort of the personality or the outcomes, like papers and presentations of different cyberneticians to see if I ask them questions about those personalities, what kinds of things would I get out of it. And so this is just very early days on this. It's not like a final project, but I've put some of these on the GitHub repository. So I've been using two models for this, just kind of playing around with see which one is better or which one gives me better answers. I've run into some bottlenecks because I'm not paying for any of the agents, so I'm kind of trying it out with the limitations therein. So like you can't upload, you can't train it with documents that are over a certain size, which is a problem. You can only, train a certain number of documents, but I've tried to actually found a collection of letters and correspondences from different cyberneticians. I found this through the library, so I've been using some of those materials. I've also been using some of the source papers from different people. So the idea is to create something that's either an amalgam of or a different personalities of W.R. Ashby, McCullough, von Forrester, and Norbert Wiener. So we have four people, four cyberneticians who are sort of targets for this. And then the idea would be like to create maybe one agent for each, or one model for each cybernetician, or combine them into a single model. I'm not really sure yet. I'm still kind of playing around with it. But the outcome are these. So in Claude Sonnet, I did a couple. What I would do is I would train it with these source materials, then I would I would prompt it, and it would give me answers for different prompts. So the first one here is, so this was compiled in Claude Sonnet 4.5. And this is, I would prompt it with a couple of prompts, and I would get this answer. And the answer, of course, is structured in the way that you would get out of a large language model. So this is, the first prompt was, how would W.R. Ashby define variety? So this is, again, if you have trained the model on W.R. Ashby's work, he mentions variety in the very specific context that he mentions variety. The agent also can go out onto the internet and get information, so there is information there as well. So the first one is, how would W.R. Ashby define variety? And the answer is summarized as, W.R. Ashby would define variety as the number of distinguishable states or elements in a set, which is, of course, the model of variety that Ashby expounds in the Evergood regulator theorem. In his cybernetic framework, variety is essentially a measure of complexity of the number of possible states a system can exhibit. More specifically, Ashby uses variety as a quantitative concept. If a system or set has n distinguishable elements, it has a variety of n. So it's basically how many elements do you have? That's the variety. For example, a traffic light with 3 states, red, yellow, and green, has a variety of 3. The concept became central to his famous law of requisite variety, which of course is key to the Evergood regulator theorem, which states that only variety can destroy variety. In practical terms, this means that for a regulator to successfully control a system, The regulator must have at least as much variety in terms of complexity or possible responses as the system it's trying to regulate. A controller with insufficient variety cannot adequately manage a more complex system. Ashby treated variety as a fundamental building block for understanding regulation, control, and adaptation in cybernetic systems, whether biological, mechanical, or social. Okay, so that's the first one. Then the second prompt was, how would W.R. Ashby define a closed-loop ultra-stable system? And then the answer to that prompt is that W.R. Ashby would define a closed-loop ultra-stable system as a system with two levels of feedback that can adapt to environmental disturbances by changing its internal organization. And so this includes a couple of 4 key features. The first is that it should have 2 feedback loops. So remember, I asked it not how would W.R. Ashby define a closed-loop system or closed-loop feedback, but a closed-loop ultra-stable system. So ultra-stability is a concept that is not like one of the main ideas that the cyberneticians advanced, but it is like, this is something that if you go deep into the readings, you find this concept of ultra-stability. So one of the key features, of course, then is 2 feedback loops. So a primary feedback loop that operates continuously to maintain stability under normal conditions, and a secondary feedback loop that activates when the primary loop fails to maintain essential variables within their critical bounds. Number 2 is step functions. So when critical variables exceed their acceptable limits, the secondary loop triggers discrete step-like changes to the system's parameters or structure, essentially reorganizing how the system operates. Number 3 is self-organization. So this is self-organization in the sense of the cyberneticians, not necessarily the self-organization that the people at the Santa Fe Institute talk about. So self-organization, the system randomly or systematically tries different configurations until it finds one that keeps essential variables stable. Once a stable configuration is found, it persists until the environment changes enough to destabilize it again. And then they have this homeostat analogy. Ashby's physical homeostat device exemplifies this. It had primary servo mechanisms maintaining equilibrium, but when disturbances were too great, uniselector switches would change the system's parameters until a new stable configuration emerged. The ultra-stable designation refers to this meta level of stability. The system is stable not just through normal feedback, but through its ability to restructure itself when necessary. It's essentially a learning system that adapts through trial and error reorganization when faced with disturbances in its current configuration cannot handle. So it gives you a lot of sort of details of this concept. And then the third prompt is, how would McCullough and Ashby differ in their definition of feedback? So this is where I'm going and I'm asking it about W.R. Ashby, but I've also trained it on some of McCullough's correspondences as well. So it has a comparator in there. And then, of course, you can go to the internet and find not necessarily a paper directly on the comparison, but like there are papers that McCullough's written on feedback, and then Ashby's written on feedback, and so it's synthesizing that. So McCullough and Ashby have fundamentally different conceptions of feedback rooted in their distinct intellectual traditions. Warren McCullough, the neurophysiologist and cybernetician, viewed feedback through the lens of circular causality in neural networks and goal-directed systems. He emphasized feedback as part of a closed-loop system where outputs return to influence inputs, enabling purposive behavior and homeostasis. His work with Walter Pitts on neural networks focused on how circular patterns of activation could produce stable states and computational functions. W. Ross Ashby, the psychiatrist and cyberneticist, defined feedback more formally within the framework of regulatory systems and the concept of variety. For Ashby, feedback was a mechanism for variety reduction, a way systems maintain stability for counteracting disturbances. His law of requisite variety implied that feedback mechanisms must be sufficiently complex to match environmental disturbances. Ashby emphasized the regulatory error coding aspect of feedback in maintaining systems equilibrium. And the key difference here is that McCullough tended towards a more neurological and computational perspective, where feedback enables complex behaviors and calculations, while Ashby focused on feedback as a regulatory principle for stability and adaptation. McCullough explored what feedback makes possible. Ashby formalized what feedback must do to maintain viability. Both were central figures in early cybernetics, but Ashby's approach was much more abstractly mathematical, while McCullough's are even closer to biological implementation. So that's the Claude Sonnet set of summaries. The idea here would be to build a workflow where you have some set of prompts, getting the answers to those prompts, and then having revising them and doing further synthesis. So the idea is, we kind of come up with prompts, not just kind of at random, but kind of almost like, you would develop a pool of prompts and then you'd kind of refine those prompts so that you get very specific, almost like research questions. And then you put them into you use them as a prompt, and then you get some answer out. And then you basically analyze them and fact check them to make sure that they're correct. And then we have a nice synthesis around this. So this is, the idea here is to kind of come up with maybe more pointed questions that people wouldn't think to ask upon first glance, or maybe questions that people would have that are sort of detailed in terms of the literature. And I know Jesse, at one time we were talking, I was talking with Jesse about building different models trained on famous people, and you could ask the model a question and it would return the answer in the style of that famous person. And so I know a number of years ago now, we talked about the Michael Levin bot, which is some tool that someone made. They trained it on a bunch of Michael Levin's papers. And then you query the thing and it answers in the style of Michael Levin, which is interesting, but it's not like, it's not in a research pipeline. So it's just kind of like entertaining. I don't want to make it just entertaining. I want to actually answer research questions here and get into the literature in ways that, maybe we can and maybe we can't easily do. So this was the Claude Sonnet version, and then there's the Notebook LM version. This is Ashby and the Mechanics of System Variety. This has like numbers, which are, I guess, citations. If you go back to the notebook, it'll have the links. I didn't put the links in here yet, but I just wanted to put it in here so I could review it. So W.R. Ashby describes the concept of variety primarily as the number of distinct configurations or states a system can assume. He treats this quantity as fundamentally equivalent to information, using logarithmic units such as bits, binary digits, to express it precisely. So this is, of course, kind of similar to how Claude Shannon defined information. It's a little bit different, maybe, and it would be interesting to explore that more. Maybe create new prompts based on that or something else. So the key aspects of Ashby's description of variety include quantitative measurement. So Ashby defines the amount of variety or information in a system as the logarithm to the base 2 of the number of possible states available to that system. So with Shannon entropy, I guess it's similar to Shannon entropy, the way he thought about it. But he is explicit about using base 2. And if you work with Shannon entropy, sometimes people use base 2, sometimes people use base 10, and technically you should be using the number of or a log to the number of states that you have, which gives you an index from 0 to 1, and that's cleaner than just kind of reporting out a dimensionless version of entropy. But in any case, that's he's very much in the same vein as Shannon. Although I'm sure if we prompt it in a way, it might uncover some subtle differences. So basically, Shannon and Ashby shared the same idea about information and thinking about variety as a component of that. Then exponential growth is also important in variety. He demonstrates that variety of a system's possible organizations increases with extreme rapidity as the number of its components grows. So that's components n. For example, in a system of n distinguishable variables, where each can be either active or inactive and can be connected by various arrow patterns, the total number of possible types of organization grows at a rate faster than 2n2, which is, of course, n squared to the power, or 2 to the power of n squared. And so that's interesting because, that's something that, is part of this concept of variety. So then it highlights variety in biological systems. Ashby applies his measures to biology, calculating that the human genetic inheritance of approximately 50,000 genes provides 50,000 bits of variety if each gene can independently assume one of two states. However, he notes that the richness of a response is not only proportional to the input. A single bit of variety can trigger a massive pre-established complex organization within a machine. So this is, again, drawing on this, applying his idea of variety to a real-world system. And I have some interesting comments on this. So this is, very much thinking about how variety can explode in terms of its complexity as you add components. So if you add a gene, that's a bit. If you add a lot of bits, that's a lot of complexity and a lot of particular outcomes of that system. And then the question is how, what is a bit? Is it the state of a gene? Is a gene, can that be summarized in two states? Probably not. There are a lot of states within that gene that you can represent. So this is kind of a thing where, it's nice to know what the definitions are so you can work from them. Then the variety of human action. So to provide a practical measure, or to find a practical measure for the variety of human behavior, Ashby suggests counting the number of verbs in a dictionary. He estimates that a typical person has a repertoire of roughly 10,000 characteristic actions, representing the system's output variety. Conversation and the destruction of variety. So a central tenet of Ashby's theory is that an absolute system or a deterministic machine cannot generate its own variety. The output of information from such a system is exactly equal to the input it receives from its parameters. Over time, variety in an absolute system typically decreases as the lines of behavior converge towards a neutral point or cycle. These convergent junctions act as sinks where information is destroyed. So it's bringing in a little bit about complex or dynamical systems in here, where you have limit cycles and other types of attractor basins. And it's kind of interesting. You could ask it again, how does Ashby's concept of variety square away is a good prompt, but square away with dynamical systems theory, limit cycles, attractors, things like that. Then there's the requirement for adaptation. So Ashby suggests that for an environment to be adaptable, it must not be total chaos of infinite variety. Instead, the world must contain a large proportion of part functions, which allow the environment to be functionally divided into smaller, manageable subsystems that an organism can adapt to independently. Then ultimately, Ashby views variety as the raw material of regulation. for a system to remain stable in a changing environment, it must possess sufficient internal variety to counter the variety of disturbances it faces. So that is on systems variety. Then Ashby step functions. So this is, I guess, I can't really remember what the actual prompt was here. But so this continues on. In the cybernetic theories of W. Ashby step functions, often referred to as breaks, are the fundamental mechanism that allows a system to alter its own internal organization to achieve adaptation. In what Ashby calls a mixed system, variables are categorized into a hierarchy. Null functions, permanently constant. Step functions, constant for intervals but subject to sudden jumps. Part functions, constant over finite ranges. And full functions, which are continuously varying. The specific roles of step functions in these systems are as follows. So there are 5 here. And again, we're talking about, systems and change and adaptation. This is sort of almost like we're describing something very similar to like a phase transition in a biophysical or a physical system. So we're thinking about these discontinuities and change over time. So the first is parameters of organization. Step functions act as the parameters of organization for the continuously varying variables or full functions of the system. While the full functions represent the immediate behavior of the system, the step functions determine the set or field, the rules of interaction, in other words, under which these variables operate. A change in step function value effectively transforms the system into a different machine with a new set of behaviors. The second is the mechanisms for breaks in adaptation. Step functions are the essential components of ultra-stable and multi-stable systems, triggering change when the system's vital variables, essential for survival, exceed specific limits, defined as critical surfaces or break surfaces. A step function suddenly jumps to a new constant value. Trial and error. This break resets the organization of the system, providing a new field for the variables to explore. This continues in a trial and error fashion, described by Ashby as heads I win, tails we toss again, until the system strikes an organization where the variables remain within the safe bounds and a stable equilibrium is reached. Number 3 is simplifying the search for stability. In a mixed system, step functions contribute to the efficiency of finding equilibrium. Because step functions are constant for finite intervals, they are considered to be already in equilibrium by definition. This reduces the dimensionality of the de-adjustment problem. The system only needs to adjust its continuous full functions relative to the fixed values of the step functions. Ashby noted that this significantly increases the probability of a system reaching a stable state quickly. Number 4 is enabling localized adaptation or multi-stability. In more complex multi-stable systems, step functions allow the system to adapt in bits rather than all at once. Because step functions only affect certain parts of the system, a break or change in one area can occur without necessarily disrupting previously established adaptations in other areas. This is functionally similar to how genes operate in an organism. A mutation in one gene can alter a specific trait without collapsing the entire biological structure. And then finally, social and biological representation. Ashby applied the role of step functions to broader contexts. So in a social system, the passing of a new law represents a step function change that occurs when a social variable exceeds a critical threshold, such as a crime wave. And so this is, again, thinking about these broader systems and how Ashby's ideas apply to that. Step functions are also the neurophysiological equivalent of genes, provided that by the gene pattern to protect the organism's vital variables through inherited or learned adaptations. So we have this sort of summary of systemic adaptation and thinking about Ashby's views on adaptation, which I think was sort of the original prompt for this. And then finally, we have a prompt on the dynamics of closed-loop systems. So this is where I actually asked it about Ashby's views on closed-loop systems, just that specific thing. And so then, this kind of gives detail on Ashby's views on this first-order closed-loop feedback that we often think about as sort of a central kernel of cybernetic regulation. So W.R. Ashby would describe closed-loop feedback primarily as a state of effective two-way interaction between components within a system. He defines feedback as being present if we can find two variables that are dependent on the other. This interaction forms a circuit where the behavior of one part is influenced by the other, and this influence eventually returns to the first part. Ashby identifies several key characteristics and insights regarding closed-loop feedback. The first is feedback as a closing link, so it provides closure. Drawing in the theory of servo mechanisms, he notes that a human operator can be considered part of a control system, acting as the closing link that takes account of the difference between actual output and desired output to alter the input. Then we have the necessity of oscillation. So Ashby posits that if variables of an absolute system undergo a recurring cycle of behavior, feedback must be present. He argues that variables cannot be interconnected in a way that produces oscillation without forming a circuit. Feedback and goal seeking. While many associate feedback with purposive behavior, Ashby argues that goal seeking behaviors do not necessarily imply feedback. Simple systems without feedback can still return to a central state when displaced. However, a powerful acting servo mechanism utilizing feedback can add a powerful stabilizing effect, making a machine more irresistible to opposition and ensuring it converges to zero error more rapidly. Critique of negative feedback. Ashby considers the concept of negative feedback to be too limited and simple to serve as a fundamental concept in general systems. He demonstrates that it is algebraically possible for positive feedback to result in stability and for negative feedback to result in instability, depending on the values of the coefficients within the system's matrix. Feedback is a selective change mechanism. In his theory of the ultra-stable system, feedback is the mechanism by which the system perceives pain or a threat to its essential variables. This feedback loop informs the system that its current internal organization is failing to maintain stability, and thereby triggering a reset or change in step functions until a new state of equilibrium is found. Feedback through the environment. Ashby emphasizes that a complete dynamic system often includes the environment as a feedback link. For instance, a person driving a car is part of a functional loop where their actions affect the environment, which is the car's position, and the environmental feedback, which are visual signals from the road. This environmental feedback travels back through the driver's brain to correct the initial movement. So ultimately, Ashby views simple feedback as a subset of more complex reacting circuits. He notes that for part of the system to behave with more stability than it possesses intrinsically, feedback is a necessary condition. So I'm keeping these in this model queries folder. I'm going to elaborate at the README. I'm going to elaborate a lot of the details about the models. What's interesting about this is I prompt it with something and it gives me this output, and then it's interesting that you can find things that are really intriguing to maybe things we were talking about in the group, and then find that little thing and query that and keep building from there. It also makes me think that maybe I want to build a Claude Shannon bot as well, or a Claude Shannon model, where we have every time we kind of bring in a new person into the conversation, bring that in, or build a customized model with just Ashby and Shannon, and just kind of refine things like that and see what we come up with. Because it's a lot of stuff that Ashby wrote a huge number of things in his career. And like just kind of, all his notebooks, everything, those are actually all online and they're available through the University of Illinois Library, where, he had his notebooks, he had like all these concepts. Some of them he followed up on um, in papers that we can read, and some of them we can't. So it's nice to have a tool that can extract some of that and kind of make connections in ways that you might not be able to make at first glance, and then kind of build from there. And then that builds upon something you can then research later in other ways, and kind of verify a lot of it, and um, just have a richer synthetic experience.
I never tried Leavenbot.
Yeah.
Well,
yeah, it's
certainly. Well, you got enough Levin video that you could actually make an AI video of him talking.
Oh, good, yeah, definitely.
But yeah, it's interesting when you with someone who's got a lot of text, you can make something that is. I forget what this channel is, but it's somebody made an AI Christopher Hitchens.
Oh yeah.
and on YouTube, and so they've got that same, they've got his diction just perfectly.
Yeah.
like it's talking like him. It's got his turns of phrases and biting wit.
Yeah.
or like cutting attacks, and like that is certainly something where they go back. It's crazy how long, like you've got video of him going back to recordings of him going back to the 80s, right?
Yeah.
So it's just like, I think it's one of those things where it's just like somebody who's been a talking head for as long as he has, like you can actually capture quite well.
Oh yeah.
And even though you've got him talking about, Venezuela or something like that, like something in the like it sounds exactly like him. So that's interesting. And yeah, now, like how can you release that for good? In the sense of like what goals? So the Christopher Hitchens thing, right? It's just like yes, it's kind of nice to have someone cutting down your enemies.
Yeah.
but I'm not sure the productivity value of that.
Right.
What can we learn from one of these bots, if you will? I'm really curious on the Brain GPT, right? So this is the Brad Love project that is trained on neuroscience papers to make predictions about a new study. So it's like you give it a an experimental design plan, and then it's trained on all these papers, and it makes a prediction of what you'll find.
Okay. Yeah.
For instance, you know, um, and I think the Brad Love idea here is that, yeah, that it would be, a useful assistant. I mean, like that it could potentially point out something uh, problematic with your design.
Right.
You know, uh, or that you're missing a control condition or something like that.
Yeah.
Um, so um, it's at least one example of like somebody who's tried, has been thinking about. Somebody posted in NeuroTechX's Slack about um, an EEG RAG. So what is this retrieval?
Oh, right.
What's the A?
Augmentation and generalization or something like that.
Okay. Um, so it seemed to be like suggesting papers or something, and I was just like, okay, I still wasn't quite sure what it was doing, and then I said, okay, so like one of the co-founders, NeuroTechX, had a paper about deep learning and EEG back in like 2018 or 2019 or something like that. I was like, would this, like, is this something where um, I could, like, could I put together a review paper of of on deep learning EEG easier, or I still wasn't quite sure. Um, what a bot trained on EEG papers would be able to um,
Do yeah.
he would be able to do. I mean, he said like it could suggest interesting papers or something like that. I was like, I mean, I honestly find, I find Gemini's recommend, like if I set a problem of like, you know, who's working on um, a variational inference or like a simulation based inference approach for tissue microstructure, um, that has some other particular detail. Like I find it quite interesting how close close a find that Gemini can do that wouldn't have come up with my kind of keyword search on PubMed.
Right.
Like it wouldn't have come up that way. Like you almost needed, yeah. It's like it definitely seems to be trained on the papers.
Yeah. So yeah, you can like build a RAG embedding from different sort of customized sources, and then use that as sort of a way to. I mean, in one way, it's self-referential because it's kind of like this is what I'm trained on. This is kind of the world of what I want to know. But like on the other hand, it does kind of cut through, like it shortens your time to, because like in a keyword search you're oftentimes constrained by your keywords, and getting them exactly right, or finding things that
Yeah. Yeah.
they may be way down in the list versus at the top of the list, things like that. So
Yeah.
I haven't really explored it that much, except to say that like that's like there's some uses that obviously exceed keyword search. Yeah.
Yeah. I've really liked it. I mean, I've found it to be quite spot on, um, in finding similarity, finding a deeper similarity.
Yeah.
And that means, but potentially, like the person's not necessarily working on the area that I'm talking about, but computationally, they're using an approach that I should learn from,
Yeah.
which is pretty cool. I mean, in some of these cases that like I said, like I've been using the agentic development to do the rapid, so it's just like find me an approach and that comes with an open source code base, right?
Yeah.
And then I can wrap that and then use it as a test oracle or etc.
Right.
And yeah, again, it's been um, uh, you know I don't uh, I'm I don't know if I'm ready to pay $200 a month for
Yeah.
the the
Full awesome power of
well, I was gonna say, not for the chat service, but so Edison Discovery, or what was, I forget what the company. So Future House
okay.
is this like Schmidt Futures project to do like scientist, sort of an AI scientist. And so, and the idea is that like you pay 200 a month and you get some amount of credits that you can run, and they're definitely training on papers, right? Now, yeah, I, I, I don't know whether I'm ready to put down $200 just to satisfy my curiosity on how that would be different. you know, I feel like these models are already trained on all the papers anyway. Um, uh, yeah, yeah, but still on the hunt for finding some value here for using up all our water
Yeah.
and
Well.
energy resources.
Yeah. I mean, and the thing is like, you have very specific things you want to know. You want to make sure. I don't know what the training set is that it might go out on the internet and find things, but I guess the having the local kind of training refines it down to, it gives it maybe more specific pointed information that may or may not be in the original training set. So that's kind of one of the advantages of using local training. But yeah, I don't know. I don't know what the actual. I mean, like I said, the first thing you would want to do in using it in a research context is figure out the sort of the workflow for how you want to use it, and then you understand kind of where its place is a little bit better. Um, so things like finding prompts, much as it's not using it as like a search engine, but it's asking it pointed questions, getting structured answers, and then refining those structured answers with additional prompts, finding the interesting connections, um, and then being able to go from there. So yeah, yeah, it's just so this is just an experiment, and I'm going to keep working on it, and we'll see where it goes. I think it is in the spirit of cybernetics, because you're building these feedback models and you're using machines, intelligence augmentation to do things.